Good afternoon all. In the previous sessions, we have seen bidirectional associative memory, learning algorithm with activation functions, how that activation functions will work. So in today's session, we will see the bidirectional associative memory with numerical example, how that algorithm will work. So let us take one example. So the given problem is construct and test a bidirectional associative memory network to associate the letters E and F, that is English letters E and F, with simple bipolar input output vectors. Here bipolar input output vectors that they have mentioned. So target output for E is equal to -1, 1, and for F is equal to 1, 1. Display matrix size is 5 by 3. Input patterns 5 by 3 input patterns are as shown in figure. So the figure shows that with asterisk symbols are there, right? So with asterisk symbols, it display like E, the first pattern. So second pattern with asterisks, it represents like F. The target for E is -1, 1. Target for F is 1, 1. So coming to the solution, let us take that. We'll see how that pattern will come in bipolar input output pattern. Let us take for input pattern, let us see the first E pattern. For E pattern, sample pattern or input pattern will become asterisk will become 1 plus 1, that is, and dot with green color. In the E pattern it is right with asterisk and dots. So asterisk represents the +1 and dot represents the -1. So to represent that in the vector form, input or sample pattern will become opposite to the E. So in the first row for E pattern, there are 3 asterisks. So 3 plus 1 should be given. That means +1. It is nothing but simply have written here as 1. 1, 1, 1. Then in the second row, asterisk dot dot. That is nothing but 1, -1, -1. Then in the third row, 3 asterisks. So 3 ones, 1, 1, 1. Then again in the fourth row, asterisk dot dot. That is 1, -1, -1. In the last row, 3 asterisks. That is 1, 1, 1. So that is nothing but E sample pattern from the given figure. In a similar way, for F also, asterisk represents the +1, dot represents the -1. By seeing that figure, from that figure we can represent the vector form like the F pattern, F figure. If you see F pattern, that can be represented in the vector form. Opposite to the F represented as asterisk represent the +1, right? So in the first row, 3 asterisks, that is 1, 1, 1. In the second row, 3 asterisks, again 3 ones. In the third row, asterisk dot dot, that represents 1, -1, -1. In the fourth row, asterisk dot dot, again it is +1, -1, -1. In the fifth row also, asterisk dot dot, it represents again 1, -1, -1. So these are the input patterns for E and F. Already target patterns are given as for E -1, 1, for F 1, 1. Let us assume the weight corresponding to the E pattern is W1, weight corresponds to the F pattern is W2. So if you see the earlier E input patterns, it overall it represents that 1:15 matrix. For F also it is 1:15 matrix. Target vectors are 1:2 matrix, and for F also 1:2 matrix. So first we'll see, let us take, there are two layers, right? One is X layer and the one is Y layer. In the bidirectional associative memory, we have two layers. One is X layer, input out in the input output pattern. One is X layer and the one is Y layer. First we'll consider X as a input vector, Y as a output vector. So at Y we have targets. The targets were given for E and F, that is -1, 1 and 1, 1. And already from the figure we got that input patterns for E and F with 1:15 matrices. So now target pattern is equal to, as per the equation, target pattern is equal to summation of weights into sample pattern. If you want to, first we'll find out that memory part. Memory part is nothing but weight matrix. To find out that weight matrix, here from the same formula, weight matrix is nothing but that sample pattern or input pattern will go onto the other side, means it will become transpose. So S transpose of P into T of P. S transpose of P means already sample pattern or input pattern were given or we obtained as 1:15 matrix. Now it will become 15:1 matrix. If you see, for E, input patterns are is represented with 1:15, right, under input S of P. So now if it is transpose means it will become 15:1. For F also it will become 15:1. So that's what here I have indicated. So W1 is equal to, first we'll see the W1 matrix. W1 matrix with respect to the E. With respect to the E, what is the sample pattern in the previous slide? So that's what here I have indicated, that in the transpose form. Now it becomes 15:1. And corresponding target pattern is -1, 1 for E vector, right? So now with that you will get the W1 weight. W1 weight is equal to S transpose of P into T of P. For E pattern, so S transpose of P, we already got it with the transposing the earlier E pattern, 15:1. Now target pattern is -1, 1. By multiplying these two, you will get the 15:2 matrix. In a similar way, to find out the W2 matrix, with respect to the F pattern, right? Already for F pattern, we find that sample vector. But that sample vector is in 1:15 matrix. If you transpose that 1:15, it will become 15:1 because S transpose of P into T of P as per the formula. So you need to transpose that sample vector or input vector. That's why here again you got 15:1 in the previous slide. The last row is nothing but with respect to the F, right? That only on the right side opposite to the W2 in the transpose form I have represented here. So 15:1 into corresponding target pattern is 1, 1. So by multiplying these two, again you will get the 15:2 matrix as shown in the figure. Now you got W1 and W2. Both the weights you got it. Overall weight or overall memory is nothing but by adding these two vectors or by adding these two weights you will get the overall weight. That is nothing but now memory. So W is equal to W1 plus W2. By adding the earlier W1 vector, which is in the form of 15:2 size, and W2, which is in the 15:2 size, will be added and we will get overall 15:2 matrix as shown in the slide. So now you got overall weight matrix. To find out the net output, sorry, here net input at corresponding neuron we need to find out, right? To find out that net input, simply you multiply the corresponding weight matrix, overall weight matrix, with the corresponding sample pattern. For example, if you want to find out the net input with respect to the E, means E input pattern will be multiplied with the weight matrix as per this formula. So already we have seen this from the starting, how to find out the net input, corresponding weight matrix into corresponding inputs, right? So that's what we are doing here. To find out that net input, if you want to test the E pattern, you take the corresponding E pattern input. E pattern input in 1:15 already in the first slide we have given. So that 1:15 input pattern into here corresponding weight matrix, overall weight matrix. So that is in 15:2. By multiplying these two, 1:15 matrix and 15:2 matrix, you get 1:2 matrix as -12 and 18. Now you got net input. After we got that net input, what we need to do? We need to apply the activation function. So if you apply the activation function, overall output y is equal to function of function of net input y in. So how that activation function will work, that's what we have seen in the previous slides, previous sessions. That is nothing but for bipolar network, if net input is less than 0, it is equal to -1. If it is greater than 0, it is equal to +1. It is equal to 0 means it is similar to the yin, right? That's what we have seen in the activation functions. So here -12 is less than 0. That's why at -12 place you get -1. Plus 18 as a net input is greater than 0. Yin is greater than 0 at the second place. That's why you get at plus 18 place you get 1. -1 comma 1 is the overall output. So if you see the what is the target output for the E pattern, that is -1 comma 1 only. Hence the correct response for E pattern obtained here. So that's what the verification. Now you got the E pattern correct response. In a similar way, we'll do it for the F pattern also. To find out the F pattern, again you need to do the net input. Yin is equal, with respect to the F pattern, what is the input pattern? That need to be multiplied with the overall weight. So here for test pattern F, again we need to do the net input. That Yin is equal to input pattern what we obtained in the first slide, that is 1:15 matrix. For F pattern will be multiplied with the overall weight matrix 15:2. Then if you multiply these two matrices, you will get 12 comma 18 as Yin. That is nothing but net input. So again for the bipolar network, if you apply the activation function, overall output y is equal to function of net input. 12 is greater than 0, that's why you will get 1. 18 is also greater than 0, that's why you will get 1. 1 comma 1. So your target output also 1 comma 1 only. Hence the correct response for F pattern also obtained. That is nothing but your actual output is matching with the test pattern. Actual output is nothing but here 1 comma 1. It is matching with the target pattern also. Target pattern also it was given as 1 comma 1 in the problem statement. So as a second cross check or second way of observation, so earlier in the first instant we were consider X as an input layer, Y as an output layer. Now you consider the Y as it is bidirectional associative memory. You take the Y as an input layer, X as an output layer. For the same given problem, if you take the Y as an input pattern means at Y they were given the target vectors. For E pattern they were given as 1 comma 1. For F pattern they were given as -1 comma 1. Those are the target vectors, right? If you take that as an input to the Y layer, here you need to get the output from the X layer. This is nothing but feedback again. That means you need to get the output as E pattern, whatever the earlier 1:15 matrix is there, right? So that 1:15 matrix you need to get it as a output by taking the target vector, that is 1:2 as a input. And so far what we have seen is we have taken 1:15 matrix, that is E pattern, as a input vector and 1 is to 2 matrix target vector as a output vector, we got it. But here in a reverse way, 1 is to 2 you take it as a input, 1 is to 15 try to get it as a output. For that, only one difference you need to observe here in this you need to follow. If you take the y vector as an input or y layer as an input vector, your weight matrix when y vectors are used as an input is obtained as a transpose of weight matrix when x vectors were presented as a inputs. When x vectors were presented as a inputs, whatever the weight matrix you got it. What weight matrix we got it? Overall weight matrix we got it in terms of what is the size of that overall weight matrix? 15 is to 2 weight matrix we got it, right? So the same weight matrix what you obtained during the x to y, that you need to do the transpose and you need to use it in the feedback also, but you need to do only transpose. That's why here when you do the transpose of overall matrix, earlier what you got here, your overall W 15 is to 2 you got it from x to y matrix, x to y pattern, right? Here x layer as input, y layer as a output. So this you need to transpose and you need to use it when you are doing the problem from y to x. So that's what here I have done. When you do the transpose of that weight matrix, 15 is to 2 will become 12, 2 is to 15. The same numbers here I have represented, but only the size will change from 15 is to 2 to 2 is to 15. Again, testing the network. To test the network, first we'll see for E pattern. For E pattern, what is the input? 1 is to 2. The target need to be taken as an input, right? For E pattern, now target is nothing but minus 1 comma. That we need to take it as an input. Now minus 1 comma 1 as an input. When you are computing that net input, y in is equal to corresponding input into weight matrix transpose, the transpose of weight matrix. Earlier we have taken only weight matrix. Now you need to consider the transposed weight matrix. So corresponding input is nothing but minus 1 comma 1. It is in the size 1 is to 2 into weight transpose matrix, that is in 2 is to 15. Now you will get the 1 is to 15 matrix as a y in net input by multiplying those 1 is to 2 matrices and 2 is to 15 matrices. You will get overall 1 is to 15 matrix. If we apply the activation function to this net input, overall y is equal to function of y in. That you will get it as, in the bipolar network, what do you need to do? When 2 is greater than 0, you need to consider it as 1. If it is greater than 0, the number is greater than 0, you need to consider the plus 1. If it is less than 0, minus 1. Based on that, these numbers at overall y has written. So this is similar to the corresponding E pattern which were we represented by seeing that E pattern. In the first slide we have shown, right? We obtained asterisk we were taken as plus 1, dots we were taken as minus 1. The same pattern we got it here. That means this, if you convert into the 5/3 matrix, you will get the E. Hence the correct response obtained. In a similar way, test the same thing for the F pattern. Now input for the F pattern. In 1 is to 2, what is the input pattern? That is 1, 1, 1. Compute the net input by using that 1, 1, that target pattern as an input, which is 1, 1 as an input. If you consider y in is equal to x into W transpose. Already W transpose we got it. Input also we know 1 is to 2 into 2 is to 15, 2 cross 15 matrix. If you multiply these two, you will get the net input. The net input will be applied to the activation function, then you will get the overall y. Overall output y is equal to function of y in. So here, by as per the activation function rule, if it is greater than 0, as all plus 2's are greater than 0, then that can be replaced with the plus 1's. Minus 2's are less than 0, that can be replaced with the minus 1. Then you will get the overall y as 1 1 1 1 1 1 1 minus 1 minus 1 1 minus 1 minus 1 1 minus 1 minus 1 in 1:15 size. So this is similar to the F pattern what we obtained in the first slide of this presentation. So here plus 1 represent the asterisk, minus 1 represent the dot. If you convert this into the 5/3 matrices, 5/3 pattern, then in the form of asterisk and dot, it will replicate the F pattern. Hence this is also correct response for the F pattern. So by doing like this, we can test the bidirectional associative memory in both the direction from x to y and y to x. From x to y, we have taken E as an input pattern and target pattern were achieved. We have taken target pattern as an input at y layer and we obtained the E and F as a output. In both the direction, we got the correct response. Thus, bidirectional associative memory network has been constructed and tested in both the direction from x to y layer and also from y to x layers. So this is all about the numerical example explanation for the bidirectional associative memory. Thank you all.